Hello everyone. Today we're going to solve together a very famous problem that has been circulating on math forums. Personally, I really liked this problem and I wanted to share it with you. Some people on the forums were curious about the solution, some solved it incorrectly, and some approached it from different angles. I will explain my own method. The question goes like this. P is a natural number, and it is given that p and p squared plus 8 are both prime numbers. Under this condition, we are asked to prove that p cubed plus 4 is also a prime number. In these types of problems, if you don't have much information, you usually try to collect some data first. That way, from the data, you might recognize a useful pattern. Let's do the same. Let's place the question on the left and build a table on the right. Now let's assign some prime number values to p and see how the other two values change. For example, for p equals 2, we get p squared plus 8 equals 12, and p cubed plus 4 equals 12. For p equals 3, they become 17 and 31. For p equals 5, they become 33 and 129. I carried this out up to 17. The problem requires that p and p squared plus 8 are both primes. We already chose p from prime numbers, so let's check whether p squared plus 8 is prime. At the beginning we have 12. That is not prime because it equals 3 times 4. Next, 17 is prime. Very good. The problem says if these two are prime, then p cubed plus 4 must also be prime. We get 31, and that is prime. So we've found what we are looking for. Let's highlight this in a green box and continue, because this is not yet a proof. For p equals 5, p squared plus 8 became 33. That is not prime, since 33 equals 3 times 11. For p equals 7, it became 57. Not prime again, since 57 equals 3 times 19. It seems a pattern is forming. The next value, 129, is also not prime, because it equals 3 times 43. The others also turned out to be multiples of 3. So can we say that for prime numbers greater than 3, p squared plus 8 is always divisible by 3? This part is actually the key idea of the problem. In fact, yes, we can. Why? Because let's say n is a natural number. Then the n modulo 3, in other words, the remainder when n is divided by 3, can only be 0, 1, or 2, right? But if you look at n squared modulo 3, you will see something different. For n equals 0, the result is 0. For n equals 1, it is 1. For n equals 2, n squared equals 4. But taking mod 3 again gives 1. So the square of any natural number is always congruent to 0, or 1 modulo 3. Alright, but this is for all natural numbers. Our equation is a bit different because p is a prime number. If p is prime, then its modulo 3 can only be 1 or 2, right? Because if it were 0, that means p is divisible by 3. But a prime number greater than 3 cannot be divisible by 3. At the same time, we already saw that the square of a natural number modulo 3 can only be 0 or 1. The intersection of these two sets is only 1. This means that the square of a prime number is always congruent to 1 modulo 3. Now, if we add 8 to this, we get 1 plus 8 equals 9, which is congruent to 0 modulo 3. And that means, for every prime number greater than 3, p squared plus 8 cannot be a prime number. Therefore, this part of the table does not satisfy the condition given in the problem. So, in fact, there remains only one possible value, which is p equals 3. Yes, I think this was a really nice and challenging question. If there is anything you didn't understand, don't hesitate to ask. See you in the next lesson.